theoretical tool. But I want to start by finishing what I was talking about yesterday. So what we saw yesterday is that ground states of local Hamiltonians, okay, obeyed this scaling of entanglement entropy, which was L to the d minus 1. So here we'll work in d space dimensions. Okay. And we call this the area law. And this was valid for both gap Hamiltonians and what we call gapless of type 1. And that had to be compared with, the generic state in the same Hilbert space where we had this L to the d, or volume law. And we also saw that there were, so this area law, there were small corrections sometimes, this or a logarithmic correction to it sometimes. And this happened with, in the case, what we call gapless of type 2, which means that there is a d minus 1 dimensional Fermi surface, or more generally, a manifold of 0 modes. Okay, the dispersion relation vanished in a d minus 1 dimensional manifold. Okay, so we saw that yesterday, and then we started playing with toy models that were aiming at reproducing this type of behavior. And one of the toy models we explored was in 1 dimension, was giving us this logarithmic scaling that we see in critical systems. And now what I want to do is I want to complete this example. Remember that we saw yesterday, or we argued, was that for a critical case, critical system, we would invoke scale invariance in the form of saying that each scale, length scale in the system, was contributing an equal amount to the entropy of a block, meaning we had short distance contributions, okay? But at the next length scale, we also had a contribution. And then in the next scale, we also had a contribution. And what we were doing was we were adding contributions. So the total entropy for a region of size L in this case is equal to 8, was equal to 2. That was because we had two boundaries, and the contributions were coming from the boundary, 2 times, and then the number of length scales that would contribute to it. And in general, here we had log 2L contributions, because what we're doing when we count length scales, what we're saying is we divide effectively the region into 2 every time. Okay, so that gave us this 2 log 2L. Okay, and that reproduces the scaling that we have been seeing for the entanglement entropy in critical 1D critical chains and systems of free fermions. Very good. So now what I want us to consider is what happens if, instead of being at criticality, if we have a finite correlation length. Okay, so critical scale invariance. Now let's get outside criticality, and so let's remove this and say, suppose that we have correlation length, a finite correlation length. And so in this time model, what we're going to say is if there is a finite correlation length, we will only have entangled singlets. Remember, these were singlet states up to that correlation length. Okay, so if we say, for instance, that the correlation length here is given by a distance like this, okay, so if this is our correlation length, then when we compute the entropy, the contribution to the entropy, we'll have this one, but this one disappears, okay? Disappears because we just define our extended toy model for systems with a gap now will be such that we only have singlets up to that correlation length, okay? And let's see what that implies then for the entropy. So obviously in this case, in this calculation, well, yeah, we would be missing some contributions. So let us look at how this looks. So suppose that we have this correlation length that we define to be, say, 4 spins. So let's take that toy model and compute again the entanglement entropy as a function of L, okay? So if the region A is small, then I get what I expected, okay? So S of L S of L equal to 2 is 2 times 1, as before. If now I compute a larger region, then I have nearest neighbors, the first contributions for short distances, but I also have the contribution from a block, okay? So now I'm putting all the contributions in one drawing. I don't want to have to draw too much, right? So in this case, the entropy for when the region is of size 4, it's going to be 2 times, and then we get 2 contributions, okay, from 2 different scales. That's because the size of the region we're looking at is still not larger than the correlation length. But now we hit L equal to 8, and when we look at the entropy for L equal to 8, we have the short distance contribution, the next distance, so the contribution from the next line of scale, but we have to stop, right? Because we already said that the next contribution is no longer present, because we are not, this toy model does not have singlets at distances that are larger than the correlation length. And so what we see is that when we now plot SL, the entropy, for a block of size 8, we have 2 times 1 from shortest distances, 1 from the next one, and 0 from the other correlation, the other length scale that we would consider. And so you can imagine doing this for L equal to 16, and we'll find the same. It's 2 times 1 plus 1 for short distances, and no contributions from longer distances. Okay? So in general, what we see is that we have that the entropy now is 2 times, and then 1 plus 1 plus many zeros, as you need, so that there are still, we're looking at log 2 different length scales, but only the shortest ones are contributing. Okay? So let's put this all together. What we are saying is that in this case, right? In this case, what we have is that if the length of the interval is smaller than the correlation length, okay, we still have the same behavior as in the critical case. What we find is that then S of L is proportional to log of L. But if instead L now is bigger than the correlation length, okay, then here we were growing 1, so this was 1, then 1 plus 1, but suddenly we stopped adding contributions. We stop precisely at the correlation length. Okay? So how many, if we look at this, there are log 2L contributions, but these are 0, and the ones that are non-zero are precisely log 2 of the correlation length. Okay? So let's plot this and see if it looks familiar. So we have log L. We want to plot this entropy. What we're saying is we're going to go logarithmic until we hit the correlation length, in which case we're going to go constant, right? So in our toy model now, the entropy is doing this shape. It first grows logarithmically, and then it saturates to a constant. But that's if you have done, if you did the tutorial yesterday, you probably saw this happening. Okay? So this toy model actually is getting lots of things right. Okay? Very good. So then I taught this a couple of years ago, and then there was a Psy student that wanted to see whether we can make from this toy model, this toy model is telling us something. It's telling us that the entanglement is accumulated near the boundary. Even at criticality, there are more contributions. So the contributions are coming from the boundary, and then they become more dispersed. And so what he did was to look at whether we could go back to free fermions and actually quantify this, see that the entanglement entropy of a region size L was coming really from near the boundary. Okay? And so let me briefly describe what he did. So this was Yang Chen, and that was his Psy project, and this ended up in a paper, which you can find. It's published, but I give you the archive number. And what he did, we call it entanglement contour. Okay? And it was a way of understanding how entanglement is distributed in space. So what we're saying here is that we have our interval, A, we trace out the rest, and we have the sites 1, 2, all the way to L. Okay? And remember that, well, with free fermions, this is something, a formalism developed within free fermions. We have that the reduced density matrix, rho A, is characterized by this correlation matrix. And we can diagonalize it by some unitary V. And this diagonal then, remember that contain eigenvalues, mu1, mu2, mu L. And that the entropy of this region was a sum of contributions, each one coming from one of the eigenvalues. So, and what we had here is that if we call the real space operators, fermionic operators, A1, A2, AL, then what we had is that we could define a vector. So if we define a vector of real space operators in this way, then we could define a new set of operators, C1, C2, CL, which would diagonalize the correlation matrix, for which the correlation matrix would be diagonal, and these ones were given by linear combinations of this form in terms of the real space one. And so here's what we have. We have that the entropy of the region is a sum of contributions. Okay? Each contribution comes from an eigenvalue which is attached to one of these C's. Okay? So let's see this. What we say is, on the one hand, the entropy, the total entropy of region A is equal to sum of contributions coming from these CI operators, okay? SI. And this SI is nothing but this function of mu I that we discussed, which is the entropy of 1 plus mu I, divided by 2, and 1 minus mu I divided by 2. So there is some expression for it. But the important thing is that each of these fermionic operators that diagonalize the reduced density matrix, each of them contributes makes its contribution to the entropy. Okay? We have this fact. And on the other hand, we also have that each of these operators that contribute to the entropy can be expressed in terms of a linear combination of the operators in real space. So what we're saying here is that take Ci, this operator, and we just said that it was defined in terms of the real space operators in terms of some coefficients, where these coefficients are given by some unitary transformation. Okay? So what this means is that we can actually take this CI, this mode CI, and see how it looks in terms of the real space operators. Specifically, what I mean is that we have these coefficients, so we can define some probability that the operator I is related to operator, so the ones that diagonalize the density metrics are related to the real space ones. So this gives us, if we just take this coefficient V IM and we square it, we get the probability distribution. Remember, these are orthonormal vectors. So you square them, and they are normalized, so you get the probability distribution. And so what that means is that for each operator CI, we get some profile in real space, okay? Site 1, site 2, site L. And so we look at where these operators live. So this operator can be expressed in real space operators, and the coefficients give us some profile. Okay? We get a profile like this just by looking at these coefficients. What we're going to say is that this particular operator, okay, is localized near the boundary. This is the boundary. This is one boundary. This is the other boundary of the interval. Okay? So we get a real space profile for each of the operators that make contributions to the entanglement entropy. And now we have it, because what we're going to do is we're going to look at this profile for this operator. We're going to weight it by its contribution to the entropy. Okay? And then, so what we're going to do is we're going to break this entropy. So we put 1 and 2 together, and we define some contribution S of n, right, attached to a given site, to be given by the sum over all the CIs, weighted by their weights, and the contribution that they make to the total entropy. Okay? So what I'm saying is that the guys who contribute to the entropy have a real space profile. So let's look at let's weight, let's create a quantity, an entropy here, such that that it has a real space profile itself, such that when we add over all the real space contributions, we get the entropy of A. Okay, by construction, this is the case. And now we can study, we can look at this S of M, okay? We can plot it. And what we can see is that actually this S of M, indeed, if we have an interval, this is site 1, site L. If this interval is non-critical, if we are in a non-critical system, in a gap system, then, so gap, then this profile will be concentrated, exponentially concentrated near the two boundaries, okay? And that's just what we said before, that there are only some contributions coming from the boundary. And in the gap case, in the gapless case, then what you can see when you plot, so this is S of M, right? What you see in the gapless case is that, again, there is concentration near the boundary, but going into the bulk, okay? So Sm, in this case, is saying the entanglement occurs, or it's concentrated, the entanglement to the interval is coming, again, mostly from near the boundary, but there are contributions throughout the whole interval, okay? And that's, again, consistent with the picture where we had contributions coming from all length scales. Okay, so that is, the logic here is that we made a toy model, and then it suggested some picture, and you can go back to the formalism. So this is not a toy model anymore. This is what happens with free fermions. You can actually characterize this. There was a question?
In the gap diagram there. Imagine the exponential decay.
There is an exponential
correlation decay, wouldn't it?
So this actually, yeah, if you consider a very large system interval, what you see here is an exponential decay.
And the decay rate would be the same as the correlation.
Away from the distance, away from the boundary. Yes, with the same correlation length that you expect. And here you see a power law decay. Away from the boundary. Yes. Okay. Good. So let's talk about what I wanted to talk today, 9.1. It's going to be entanglement. Entanglement entropy. EE, and universality. Okay, so there are a number of ways in which entanglement entropy is universal, and maybe the one that is more important is that what we've seen is this edge local, I wrote it in there, edge local in d dimensions leads or is attached to a ground state that fulfills the area law. And, okay, so ground state. And the connection here is, if you want, an observation by many people in different contexts. So what the real connection is there, it's not clear, but we can give it as something that needs to be taken seriously. Yes?
Do we have a proper definition of H local?
Made of local pieces.
Yeah, so what would then be a local piece? Like?
So you would consider, right. So I would say conservatively that I'm comfortable with saying that it has, so in a lattice system, have a notion of locality, of neighborhood. I say some sites are closer to each other than others. And then I have that my Hamiltonian is sum of terms, and each term only involves a local neighborhood within the lattice.
So basically it has to be creative and at infinity.
Right, so I would extend this then to say if there are longer terms that involve a finite number of sites, okay, but the sites are farther away, I want the amplitude there to decay, say, exponentially with the distance. Yes. But I don't want to go quantitative here. Yeah. Okay, so the first observation is that this is a very universal thing. Okay, it's a universal feature of ground states of local Hamiltonians, and I don't think it's an exaggeration to say that it hints at some fundamental truth of nature. Okay, and what I mean by this is the following, and we have not yet understood completely. We're only starting to understand. But in quantum mechanics, there are postulates, right? And they give you this vector space, right? You say the space of states form a vector space, Hilbert space. And then they tell you observables correspond to Hermitian operators, etc. There are postulates. And there is one postulate that is relevant to this discussion, which is that says that if you have a composite system, A and B, then the vector space is given by the tensor product. And I'm not objecting to this postulate, but this implies that when you have n spins, then you will end up dealing with a tensor product of n, say the Hilbert space of each of the spins. And I still don't object to that. But what I'm saying is that most of this Hilbert space is irrelevant, actually, to physics, okay, as you consider large n. So as we consider larger and larger systems, we have this huge Hilbert space, okay? It's huge. But most of it is both inaccessible and irrelevant to local physics. Because what we forgot to say is that there is a Hamiltonian that, we don't object to this one. Hermitian operators are describe our observables. But we have to add the notion of locality in this picture. And the notion of locality appears when we consider systems of many pieces. Okay? And this notion of locality, maybe we cannot postulate things, but we can observe that most of the Hilbert space that we've built, most of it, is not accessible. It's not. It's made of states that will not appear, that we cannot even prepare with a quantum computer. Okay? Quantum computer is supposed to prepare anything that we can prepare physically in quantum physics, but we won't be able to access. It's a computational problem. Okay? It's a complexity, the scaling. So you look at the Hilbert space, it's growing exponentially fast. If you look at a quantum circuit that will prepare any state that you want, okay, if it has a length, this quantum circuit, a depth that is polynomial only in n, it won't be able to reach all the states. There are too many states in here. Okay? So what I'm saying is take a very big quantum computer of the size of the universe. Take a lot of time. Equal to the edge of the universe. You cannot beat. This will give you it will allow you to explore the Hilbert space by some amount which does not grow exponentially in n. It will only grow linearly or polynomially in n. Okay? So this Hilbert space, maybe for n equal to 10, there is no need to go philosophical, but for large n, there is something there. It's too large. Yes.
Are you saying that some of the quantum states are not accessible if we dynamically search swipe the quantum space with given Hamiltonian? I mean, if I just give a random coefficient, I mean, if I generate the string a random number and just assign the coefficient to the state, then I think there's no reason I cannot access to the quantum state.
Yeah, I'm talking about physics. I'm talking about prepare a quantum system in an experiment, and let's agree that the best we can do is to produce a quantum circuit, or that the quantum circuit model is already encapsulates everything that we can do, right? And what I'm saying is put here, so it's a quantum circuit, this is n, okay? Now take a lot of time, say polynomial in n, not exponential, because we will only be able, okay, so the statement is that if we explore all possible states that we can create by means of a quantum circuit like that, which is what a quantum computer could do efficiently, then you will not, you count how many parameters you have here, and you see that they are polynomial in n. Okay? And there is no way that with polynomially n parameters you can produce exponentially many different states. Okay? You can tune all these parameters, and at most you reach a submanifold of a Hilbert space that has dimension polynomial in n. Okay? And what I'm saying is this is going crazy and allowing for a quantum computer, right? Which is assumes control of an individual quantum system. What I'm saying is in condensed matter, for instance, you don't find that your ground state is the result of a complex fine-tuned quantum computation. It's more of how you throw in a local Hamiltonian and you look at how the degrees of freedom are organized through a local, simple local Hamiltonian, and then you get, so a quantum circuit could violate this area law, but if you don't consider quantum circuit, but just ground states as found in nature, then you realize that there is even more constraints, that these ground states fulfill this area law.
Is the generate interaction in natural system?
Sorry?
I mean, is the generate interactions and all the correlation in natural system in our universe can be always described by the quantum circuit?
Yes, but this can describe much more. Yes. So quantum circuit, you can obtain it by just discretizing the time evolution, the Schrodinger equation. There is a unitary evolution. Now you make small steps in this evolution, and you can replace it. You can see that you can replace it with small gates, sequence of gates. Okay, but okay, so this was the kind of philosophical thing. But in addition, when it comes to universality, to be more concrete, we also see that the entanglement entropy provides access in concrete systems, provides access to information about universality classes. So what I mean by this is that you can think in the sense of an RG flow in the space of theories. So you could have some RG flow going from, you consider a space of more general space of Hamiltonians with local couplings, and this is highly dimensional space, and then you can start wondering what happens or what are the fixed points of this flow, and then you identify them with both gap phases, so fixed points. You can identify them with gap phases of matter, and also with phase transitions. Right? The unstable fixed points, the ones that there are directions away from them, correspond to phase transitions, and the ones that are completely stable correspond to gap phases of matter. What I'm saying is that each fixed point then contains all the universal features of that phase or of that phase transition, and entanglement provides us information about precisely this, about what universality class we have. And so, for instance, for gap systems, I will be talking about topological quantum field theories. And for phase transitions, we could be talking about conformal field theories. Okay, so it turns out that we can learn, extract information about such theories, which contain the universal information of the phase or phase transition, by just looking at entanglement. So let's look into that. So first, let's look at entanglement entropy in quantum phase transitions. Like conformal field theories, and we already discussed this in previous weeks, last week and this week. So what we have is that the CFT represents this universality class of the phase transition, and it's in turn characterized by the conformal data. And just to remind you, in 1+1, this was a central charge. There was this primary field with the scaling dimensions and conformal spins. Okay, these are things that we've seen these days. Okay, so let's try to think what that means. So suppose that let's consider 1+1 dimensions, as we've been discussing these days, and so imagine that you have a way of computing the ground state wave function. Okay. Let's not worry about the complexity now. So there are 2 to the n coefficients, but imagine that we have a very powerful computer, and we can do that. Now, here it is, 2 to the n coefficients, complex amplitudes. It's full of irrelevant details. This might be the wave function of a critical system, right? But how do we extract the information? How do we extract the universal information? So information we have a lot, okay, 2 to the n coefficients. That's a lot of information, more than your hard drive can handle. But let's not worry about that. The question is, how do we extract the relevant universal information that tells us exactly what phase transition we are talking about? So it turns out that, well, if we knew, say, the symmetries of the theory, we could look at order parameters, we could try to understand the expectation value of the order parameter. We could do many things. But what's really impressive is that we don't need to know anything a priori to compute the reduced density metrics. If they give me the wave function, I can compute the reduced density metrics on a region A. Okay? I can plot how, for different sizes of A, how this entropy scales. Okay? And from there, I still didn't know anything about the phase transition, the theory, or anything. I just did something mechanical, okay? And I read from here the central charge, okay? I think this is very remarkable. We didn't know anything about the theory, okay? And without any previous knowledge, we can already extract universal information, a piece of universal information. Okay, and how much have we learned? How much have we learned? So we haven't learned everything about the CFT. We have only learned the central charge, but it so happens that for central charge smaller than 1, there is a discrete set of what's called unitary minimum models. And these include, so there is an expression for m equal to 3, 4, etc. And then for m equal to 3, we have c equal to 1/2, and this is one of the guys we've been playing around. It's the Ising CFT. It's the Ising model. For c equal to, the next one is 7/10, and this is the tricritical. Ising model. For the next one is c 4/5, and it's the Potts, three-state Potts model, and so on. Okay, c equal to 6/7. It's tricritical. Potts, and so on. So what I'm saying here is that if you just, there is, for central charge smaller than 1, there is only a discrete series of unitary, if we are interested in unitary models, which are the ones that make physical sense for us, what we find is that there is a discrete series, okay? If you compute the central charge, you know what theory you have. Okay, so you completely, in this particular case, you completely characterize the CFT. So you learn everything about the phase transition after just computing entanglement entropy. That's extreme. I mean, that's for C smaller than 1 for these models. For C, for central charge, then we have already continuous. There are infinitely many. There is a continuous family of CFTs. So continuous family of CFTs. So we haven't learned everything. If you compute the central charge and you get it a 1, you still don't know what phase transition you are talking about. Okay? You know that it's within a set of infinitely many possible CFTs. You've learned something, but it's only partial information.
Is the central charge and the universality class always have one-to-one correspondence?
The answer is no. That's what I'm saying. A universality class is characterized by a CFT. That's a one-to-one correspondence. Okay? And in these examples, the central charge completely characterizes the CFT or universality class. Okay? But for C equal to 1, there are many CFTs or universality classes compatible with C equal to 1. Okay? So the entanglement entropy generically will only give us partial information about the universality class. It's good, but it's not complete. Okay, so what else can we say about entanglement entropy in critical theories? What we have is there is this C theorem, and that's some Logikov, who visited recently, actually. This is from 1986. It says that there exists, this theorem says that there exists some function C, which is positive, that if we have an RG flow, so again, this is the space of theories, we can identify fixed points. Say there's a CFT1 here, and CFT2, and then some trivial phase. So this would be central charge C1, central charge C2, and then the central, in the trivial, in a gap phase, we have, so maybe I'm going to call it gap phase, the central charge is equal to 0. And so what we have is, in the RG flow, maybe this theory, if we perturb it in a very particular way, it can flow from a CFT to another one. This CFT, if we perturb it away, will probably flow to the gap theory. And then this one, if we perturb it in a random way, it may just flow directly to the gap phase, or maybe it gets very close to the other fixed point, but then eventually it flows to the gap phase. Okay, so this is a typical situation. And this theorem says that there exists a quantity that depends, C is a quantity that depends on the couplings. Remember, this is the space of couplings, Q1, Q2 of our Hamiltonian that defines the theory. So there is a function of the couplings such that C, so that decreases monotonically, decreases under RG flow. This is one thing, and C of G alpha is constant at RG fixed points. And there, remember, fixed point, we have CFTs. And there, C is equal, so C at a fixed point is equal to the central charge. Okay, so that's a very important result. It tells us that there is that not all the CFTs are equivalent in the sense, from the RG sense, in that if this central charge, this CFT can only flow into this one if the central charge is larger or equal than this one. Okay, if this central charge was larger than this one, there will not be a possibility of flowing from one to the other, because it would contradict the existence of, it would contradict the monotonic behavior. Okay, so the existence of such C function is very important. It tells us that we cannot flow from CFT with small central charge to a CFT with larger central charge. Okay, so this was a big deal. And then it turns out that there is a version based on entanglement entropy okay, and this is Cassini and Huerta in 2006, so 20 years later. And this proof just says, actually, if you take the entanglement entropy, okay, it's a function of L, and you take the derivative with respect to L, and you multiply by L, okay, this thing, and let me multiply by 3, you'll see why. This quantity is a C function. It's one that fulfills, such that decreases monotonically. And the proof, so this is a C function. So it's not the same that was found by Zamolodchikov in his original derivation, but it doesn't matter. It also fulfills the same role. It tells you that there is a irreversibility in the RG flow. And the proof is very simple, and you can go and have a look at it. And it uses just what? Lorentz invariance. It assumes Lorentz invariance. So assumes, it's a physical assumption. I think it assumes also unitarity. But all CFTs are Lorentz invariant, okay? So what are we assuming? Unitarity is a constraint, but we're interested in CFTs usually that have a Hilbert space with positive scalar product or norm, so that's fine. And then it also uses, but this is not an assumption, it uses a property of entanglement entropy, which is called strong sap additivity. strong subadditivity. And this is not an assumption, it's a property of entanglement entropy, okay? Of the entanglement entropy. So assuming a couple of very reasonable things and taking a simple property of the entanglement entropy, you can show that this is a C function. And in particular, what this means is that if we plot, so let's do something that is close to what we've been studying. Suppose that you have the XX model, which we've discussed, that corresponds to some CFT with C equal to 1, and the Ising model, which is CFT with C equal to 1/2. So if there is a perturbation of XX model that goes into the Ising model, then what we could do is the following. We could plot the entropy, okay? So we start with this model, and remember the Hamiltonian is very simple, is sigma x, and now I'm gonna add some little perturbation here. Some magnetic field, which will depend on gamma. But this is a model that you can map it to 3 fermions, all of it. And so you could analyze it for very large systems. And what I'm saying is, for gamma equal to 0, we go back to the XX model, okay, where sigma x and sigma y have the same weights. So we would be here in this fixed point. But if you now put gamma very small, okay, but you add a little bit of, you unbalance these two terms a little bit, then this will start flow. This is a relevant perturbation of this model, and what you will see is that at short distances, the entanglement entropy doesn't react automatically, because at short distances, all the physics is still the same. Okay, you've changed the Hamiltonian just a little bit, so you would see that the entanglement entropy is growing like that. But at some distance, you'll see that it starts to departure from this 1/3 log L, and it'll switch into 1/6 log L, okay? And then it'll stay constant. So what we're saying is, when we were very close to here, we still saw the behavior that you expect from this CFT, the initial CFT. But as you consider larger and larger regions, you'll see this other behavior, which is consistent with this is Ising, C equal to 1/2, and this was XX, C equal to 1, okay? So what this version of the C theorem says, or this particular C function says, is that the behavior will, in relativistic, at least in Lorentz invariant theories, will be that the log of the entropy will always, the slope of it will never increase. The slope can only go down, okay? Stay constant at a fixed point or go down. And if you look at this quantity and you plug, so let's analyze that quantity when S of L is central charge over 3 log L, you see that indeed, let's take 3L times the derivative of this, which is C over 3, 1/L, okay? And you see that indeed, at the CFT, this quantity will be the central charge, okay? And it's a very, very simple quantity. So entanglement entropy is useful also here.
Does this C theorem hold in general dimensions?
No, very good. So it's, there are generalizations. And actually, people in the house, Rob Myers, for instance, has actively contributed to these generalizations in 2+1, for instance. So let me briefly also talk then about higher dimensions. So in D equal to 2+1, what we have is that the area law says that this should scale as, I'm doing this just for field theories or for lattices. There is a non-universal part and then a universal part. And so this is the area law. You recognize the area law here. We're talking about 2 plus 1, so space is 2-dimensional, and what we're looking at is a region of, say, a circular region of boundary or of linear size L. And then we see that the entanglement entropy, as expected, okay? I'm talking about CFT here. Okay? That the entanglement entropy is expected is proportional to the size of the boundary, and this you can again remember. There is this picture that says that it's made of short contributions and then also longer contributions, and so at all length scales, but the dominant contributions are proportional already to the size of the boundary. So we get this term. And then we get a correction, okay? And this correction can be shown to be universal. And actually, that's something that precisely Rob Myers and collaborators contributed substantially in the last few years to establish. And again, there is some F theorem, which is an analogous or generalization, higher dimensional generalization of the C theorem, which also states that this quantity can, so this is universal at the fixed point at CFT, but also under the energy flow is going to have a monotonic behavior, okay? And so again, you can establish that if a flow is to be possible between one CFT and another one, then this quantity should be smaller in the final CFT, okay? Very good. And there are many things we could talk about, and today is the last day of the week that I want to talk about entanglement entropy. So I'm just going to make a pointer here and move on. So there is this ADS CFT, or holography. There's ADS CFT correspondence or holography. And again, in the house you have many experts, such as Rob Myers or Pedro Vieira, who's teaching next. And so you should go to them for details. But the basic idea is that, again, the entanglement entropy of a region so this is a duality between a theory in D plus 1 dimensions and a theory in D plus 2 dimensions. This is a field theory. And this is a gravity theory. Okay? And the idea is that the entanglement entropy on the quantum field theory side can be computed or can be equated to the size of some minimal surface on the other side. Okay? So I don't know, I can write something here, but it's not going to be very informative. And all I want to do is to say that this is a big deal in holography. And so some of you, if you are interested in holography, there is a lot that you can that can be said in that direction. Very good. And I want to manage this last 5 minutes. Okay. So I think that, right. So I wanted to tell you also about topological order, but I don't have time. I wanted to tell you that this topological order would correspond to the gap phases, the case of gap phases, so fixed point, again, of the RG flow, but this time gap phases. And they form their own universality class. And again, entanglement entropy can be used to extract information about the universality class for systems with topological order. Okay? So it's not only critical systems, but also systems with topological order. And then I want to use the last 5 minutes to quickly discuss what we can say, what we already know beyond entanglement entropy. So remember that, so this is going to be 9.2. I want to talk about the entanglement spectrum. And so remember that when we studied at the beginning of the week, we reviewed basic background on entanglement. We defined this Schmidt decomposition So you have a system of two pairs A and B, and you can decompose it in a canonical way. We call this Schmidt decomposition. And since then, we said, oh, actually, these P alphas, these Schmidt coefficients, we said are a complete characterization of the entanglement of this bipartition. But so this was the complete characterization. But since then, we forgot about that, and we just took a very convenient and useful function of these coefficients. Okay, and we've thrown away the rest. I mean, there is much more information here than here. Okay, so working with the entanglement entropy was, if you want, necessary to simplify things and to make progress, and it's been extremely useful. So we've seen that, for instance, we just saw that you can use just entanglement entropy to extract central charge, and if we had done this topological order, there is a topological quantum field theory attached to it, and there is this total quantum dimension, which is another quantity that can also be computed from entanglement entropy. Okay, so this was really good. We're happy. But can we go beyond that? Can we take a step back and say, hey, there is more information here? Okay? And so actually, yes, this can be done. It has been done, and it has been shown to be also useful and to provide more information than just entanglement entropy. And so what we're going to do now is we're going to define entanglement Hamiltonian. So we have rho A, okay? And this is the density matrix for region A. And we can just decide, this is going to be our definition. We're going to look at this as if it was, we will regard the density matrix as the exponential of some Hermitian operator, and this we're going to call entanglement Hamiltonian. Okay, and if you want, no big deal, but if you want, the definition is minus log of rho A, okay? And the base log should be 2 for consistency, but I'm not going to worry about that. So what we're saying basically is that if rho A is U diagonal P1, P2, P whatever, then K is unitary, and then in the diagonal what we're going to have is minus log of P1 minus log of P2, etc. And we're going to call this minus log of P alpha, okay? We're going to call this E alpha entanglement energy. Okay? And so far, these are definitions. And what's very spectacular is that these entanglement energies, the spectrum of the entanglement Hamiltonian, actually, in several situations, reveal a lot about the physics of the phase or the critical point. And in particular, since we've been able to see, CFTs, remember that for C, so let's go to CFT in 1 plus 1. We have this central charge equal to 1. We said there are infinitely many. There is a continuous family of CFTs with the central charge equal to 1. Well, it turns out that if you look now, you take the wave function. We said if you look at entanglement entropy, you determine that C is equal to 1. But if you look at the entanglement spectrum, okay, you can actually characterize what's called the compactification radius, some parameter that parameterizes all this family, okay? And so you can determine some compactification radius. And know which CFT you have, okay? So it was good that we, to make progress, we just focused on one quantity, but actually don't throw away the rest of the information, because the full entanglement Hamiltonian has a lot of information in it. OK, so I think I'm going to have to cut it here. This week, what we've seen is this bipartite entanglement. We've talked about entropies, entanglement entropies, and Schmidt, more generally, all the Schmidt coefficients that now we just suddenly realize, oh, OK, there is useful information if you take the log of it. This spectrum of energies informs you of what CFT you have. And so the big picture here is that we can use entanglement as a diagnose. Okay, it's a theoretical tool. It's not just it's not the result of a calculation only. It's actually some quantity from which you can learn about the physics of the problem. And this all started with this area law, and then just by analyzing carefully the area law, we see that sometimes there are corrections, and these corrections, or there are coefficients in front, which are universal. Maybe the leading term, maybe there is some correction which is universal, as we saw in higher dimensions up there, somewhere. Yeah. OK. But next week, we'll go back to looking at this area law from another perspective, which is, can we exploit the fact that these ground states are not very entangled? Okay? Can we exploit it computationally? Can we devise some strategies, computational strategies, to actually efficiently simulate these ground states? Okay? All right.